Hey everyone, it's Mr. Privet. I'm excited to be here going through the final question of the 2023 FRQ. If you've stuck with me all the way, gone through 1 through 5, I'm excited. We've got to the final part. It's a big one for us. So we're going to dive right into it. But thank you so much for all of y'all's support. I appreciate all of y'all, liking, commenting. It's a lot of fun to read it. And I hope that what I'm doing is beneficial for you guys and growing your knowledge of calculus. But let's go ahead and dive right into it. Part A, but let's read it. It says, consider the curve given by the equation 6xy equals 2 plus y cubed. And part A says, show that dy dx equals 2y over y squared minus 2x. So we start out with the equation 6xy equals 2 plus y cubed. And we're trying to solve for dy dx, or the derivative of y, with respect to x. Now, one very practical thing here. If I try and take the derivative of this equation and do not get the answer that they gave us in the problem, I am wrong, right? The AP is not going to be wrong for this one. So it's important that if we do make a mistake, let's just cross it out, try it again, Let's take a derivative. Because y is not isolated, we're going to take an implicit derivative. Now on this left side, I have x times y, and I'm going to treat x and y like separate functions. So to take the derivative of 6xy, I need to use product rule. So product rule is the derivative of the first term times the second term, so that's just 6y, plus the first term times the derivative of the second term. Now the derivative of y with respect to x is just y prime, or dy dx, right? And on the right side, the derivative of 2 is 0. The derivative of y cubed is 3y squared, y prime. So now I just need to isolate y prime. So I'll subtract over the 6x, get 6y equals 3y squared y prime minus 6xy prime. I'll factor out the y prime times 3y squared minus 6x divided over, and I get y prime, or dy dx, is equal to 6y over 3y squared minus 6x. I can divide the top and the bottom by 3, and I get 2y over y squared minus 2x. And I check and see it is in fact the same, so we're good, right? We got our answer for part B. So this one just showing, do you have the ability to take an implicit derivative? Yes or no? We did. We're awesome like that. So we are good to go. So that is it for part A. We'll move on to part B. Now it looks like part B and part C are pretty similar, just in the way that they're set up. So I'm interested to see how that'll set up. So part B says, find the coordinates of a point on the curve at which the line tangent to the curve is horizontal, or explain why no such point exists. Now, I'm going to write down some information we got from the previous question, right? It was the equation, right? But then it was also the differential. dy dx equals 2y over y squared minus 2x. And they ask us, is there a tangent that is horizontal to the curve? Well, in order for there to be a horizontal tangent, the derivative at that point has to equal 0. So in order for this equation to be true, 2y has to equal 0, or more specifically, y has to equal 0. Now, you may say, oh, great, y equals 0. Yes, there must be a point, right? But it asks for the coordinates, so we need to go and find the x value by plugging in y equals 0 into my initial equation. So if I plug in y equals 0, 6x times 0 equals 2 plus 0 cubed. 6x times 0 equals 0. 0 cubed is 0, so I get 0 equals 2. So there are no solutions. So therefore, the only possible way we could get a horizontal tangent is y equals 0. That doesn't actually exist on the curve. For the curve, y never equals 0. So therefore, no such point exists for a horizontal tangent. So that is the answer to part B. But now we'll move on to part C, which, like I was saying, looks really similar, right? But there's one distinct difference. Part C says find the coordinates of a point on the curve at which the line tangent to the curve is vertical. So now we're looking for a vertical tangent. Now I'll put the same information. dy dx equals 2y over y squared minus 2x. Now for a vertical tangent, my derivative has to be undefined, right? Which also means that this denominator here, y squared minus 2x, has to equal 0. So y squared equals 2x. And this is just true in order for there to be a vertical tangent line. Now they're asking us for the coordinates of a point, right? And we saw in the last question, just because we get an equation out of this doesn't necessarily mean that that actually exists on the curve. But I have two equations and two variables. So I'm going to substitute. I'll get y squared over 2 is equal to x, and I'm going to plug in x into my initial equation. So 6 times y squared over 2 times y equals 2 plus y cubed. Multiplying this out, 6 divided by 2, I get 3. So 3y cubed equals 2 plus y cubed, or 2y cubed equals 2. Y cubed equals 1. The only real solution to that is y equals 1. So that's the y value of the point. To find the x value, I just plug it back in to this equation up there, and I get x equals 1 squared over 2. So x equals 1/2. So therefore, the coordinates of the point that satisfies this is 1/2, comma 1. And that is the only point on the curve that satisfies that there is a vertical tangent at the point. So that is our final answer there. So part B and part C asking very similar questions. One of them, does exist. We have to go find the point. The other one, there's not a solution to it. So interesting. I like it with the differential questions when they kind of ask us the two different sides. One exists, one doesn't. There's another FRQ that I'm now forgetting which year it was, but it asked like a very similar set of questions. Like B and C of the FRQ were both horizontal and vertical tangents. Are they real? And I wish I remembered which one it was. If I do remember, I'll try and mention it at the end of this video, or I might just like clip it in at the very end, But this is something that definitely has shown up before, could continue to show up in the future. Oh, here it is. Yeah, it is the 2024 FRQ number 5. So super, super similar question. If you want practice with this, like this is perfect practice. Number 6 for this one, B and C. 2024, number 5, B and C. Perfect practice for these types of concepts. But let's move on. We still have one part left to do. We're kind of breezing through it so far. So I kind of assumed that D's the hardest one, right? Normally when A and B and C are easier, we can expect that part D is going to be challenging. So let's take a look. A particle is moving along the curve. At the instant when the particle is at the point 1/2, write down 1/2, comma -2, its horizontal position is increasing at a rate of dx dt equals 2/3 units per second. What is the value of dy dt? Okay, so we see that I have a curve, there's a particle moving, and I've got a dt, right? A lot of times when I see a dt for x and y, I know I'm dealing with a related rates question, right? Now with related rates, what we do is we try and find some sort of equation, right? And then we take the derivative implicitly with respect to time. Now in this case, we don't even have to go out and create our own equation because they give it to us, right? 6xy equals 2 plus y cubed. So now if I take the derivative with respect to time implicitly, I should get an equation that has dx dt and dy dt. And maybe I can use the point to solve for dy dt. So let's take a look. Similar to how we did it in part A, the derivative of 6xy, we're going to do it using product rule. So first term times the derivative of the second term, the derivative of y, in this case, is dy dt, because we're taking the derivative with respect to time. Now the second term for product rule is derivative of the first term, so dx dt, times my second term, which is y. So that's my left side. My right side, the derivative of 2 is just 0. The derivative of y cubed is 3y squared times dy dt. And now I look at this, I've got x, y, I've got dx, and I've got dy, 4 variables, right? Now they tell us dx dt, and they also tell us x and y. So 3 of those variables are going to be solved for, leaving only our dy's to be solved for, which we should be able to do just using some algebra. So let's just plug them in. My x value is equal to 1/2 dy dt plus 6 times dx dt is 2/3, y is equal to -2, and that's equal to 3 times my y value, which is -2 squared, times dy dt. So over here I get 3 dy dt plus, let's see, if we cancel out 3, I'm left with 2. So 2 times -2 is -8. And that's equal to 3 times -2 squared, which is 12 dy dt. So now we're almost done. All we have to do now is isolate. Oh, watch the voice crack. Isolate dy dt. I subtract this over, and I get -8 equals 9 dy dt. I divide by 9, and I get dy dt equals -8/9. The question specifically said that the units for dx dt were 2/3 units per second. So in the same way, I might say units per second just to appease the AP. You know, it doesn't really say to give units, but I would probably put the units regardless. But that is our final answer. Part D was worth 2 points. Part C was worth 3, which I think is pretty great. This one felt more difficult to me than part C did, but it's fantastic. Overall, number 6, I would say generally this is an easier FRQ than ones that I've seen given by the AP. But like I was saying, if you want a fantastic question that gives really similar practice to this, look at 2024 question 5. I've got a video on YouTube for this one as well. So if you want more help on how to do questions like these with differentials, that would be a great resource to look at. But that's all we got. Thank you so much for watching. I really appreciate y'all, and I cannot wait to see y'all in the next video. So have a great one, and I'll see you later.